compare that to the solar neighbourhood where it's falling east to the. So mostly these are fairly young, fairly bright stars. I think the thing that wouldn't. I think it could have a planet that was relatively nearby. I don't think it would lose Mercury, for instance. It's not going to be tidally stripped. But because that'd be. I have to sit down and work this out. But yeah, if Pluto was attached to it, for instance, then it would lose it on its way through there. But I think these particular stars, the question of whether or not they have planetary systems might be also a function of the environment. What's that for?
Presumably, there'd be fairly massive tidal differences between the side of the star facing the black hole and the other side. You can work
that out. It would be significantly ellipsoidal as it passed through the. In fact, I think one of the things people have looked at is whether or not you can use this mechanism to accelerate. If you have a binary star that passes close to the central black hole, whether or not you would expect that binary to be broken apart by the. And you can actually have gravitational interactions that leads one of the stars moving quite quickly and the other one moving quite slowly when you have a three-body system. So there's all sorts of funny dynamics that can happen inside of the single cluster. So the other place that we've been able to see kind of close-up evidence of black holes outside of the supermassive black hole at the center of the galaxy is that we can see objects in the X-ray often that are clearly, associated with stars. They're feeding most likely from an accretion disk. And when we look at the detailed form of that accretion disk, we're looking at material that's orbiting close to the edge, to the event horizon of the black hole. And so when you say, what is the detailed spectrum that I see from an accretion disk, that's going to be a function of the light coming from this disk. The inner part's going to be moving again at close to the speed of light. And when you build that understanding back up, you again kind of realize that you're looking at something that's close to the edge of the black hole. The only difference, of course, is this is purely an artist's rendering of something. It's not actually what's, we can't actually take an image of a stellar mass black hole. In fact, that actually mentioned one more thing. We'll get there in a little bit. The other thing that is different in our understanding of black holes from the one that Mitchell would have had. So he had this idea. It turns out the French mathematician Laplace had a pretty similar idea at pretty much the same time, presumably independently of Mitchell. And so, but both of these results sort of just kind of sat in the literature as a sort of Easter egg waiting to be discovered. But the thing that really kicks off our understanding of black holes is this gentleman. And so it's obviously Albert Einstein. This picture, in fact, he's written some of them. If you're kind of an aficionado, you'd recognize the thing that he's written there as most likely some of the mathematics of general relativity. And this photo was actually taken sometime after he's an elderly man in this picture. So Einstein was, let's see, I think that is, would be born in 1873, so 1915. So he's still a relatively young chap, probably 40ish. And so there's photos of him in Germany, and he's got the moustache, but he's it's more neatly clipped. His hair's under control. This is before he's become the sort of the kind of pop Einstein as opposed to the Einstein that actually made himself famous. And so it's actually worth just kind of getting your head into the space where he would have been. So Einstein was born in Germany. He moved to Switzerland where he studied. He lived in Poland for a little while. He was recruited back to Berlin by his friend Fritz Kerr just before the outbreak of the First World War. So Einstein is working in Berlin. It's the center of the empire locked in the global war. Haber himself was inventing poison gas and getting ready to take it to the front. Einstein was trying to figure out how gravity worked at some fundamental level. So the world is going to custard around him, but he's sort of actually, it turns out, in a race with his friend Hilbert to write down the kind of final set of equations that describes what we would now call Einstein gravity. And the way that he got to this is he'd come up with his special theory of relativity in 1905. And what he was trying to do was, how do I put in his understanding of gravity into the system? Because relativity it forces you to think about how it is that you compare one velocity to another. So the kind of transformation that you would make if you were sitting in a car and your little brother's lobbing something into the front seat, and you say, how fast is the toy that my little brother threw flying and it goes into the front seat? Is it going, do I measure its speed relative to the car, or do I measure its speed relative to the road, or do I measure the speed? How is it that I work out the difference between speeds and different frames of reference? And so it turns out once you put, the special theory of relativity kind of changes our understanding of that. But when you put gravity into the picture, where you have acceleration, an object that's freely moving in a gravitational field is speeding up, but if you're sitting on that object, you don't feel that you're being sped up until you kind of sit on the floor and you're pushing back against the force of gravity. If the floor was to vanish, we'd all be in free fall just as much as we would be in space until we hit something solid. And so Einstein's general theory of relativity is an attempt to make sense of this kind of change our understanding of what's going on. And so how many people have seen a picture like this? So one problem, of course, is that there really is gravity, and you're going to explain it. So that gravity must be somehow, this is our model of gravity, and gravity's kind of somewhere down on the floor, pulling the ball down. So it hasn't really, this hasn't really explained what's going on. But the way Einstein explains gravity is he changes our understanding of what it is that time and space really are. And so if you think about Newton's understanding of time and space, or the same understanding of time and space that Mitchell would have had, he would have said that time tells you when things happen, and space tells you where things happen, but nothing happens to time and space. Things happen inside of them, but nothing happens to the thing inside. But what Einstein said was actually space-time, which is one thing, as an object moves around inside of them, then the shape of space changes as the object moves around, and that's how we know that the gravitational field is there. So if this kind of matrix that the Earth was sitting on wasn't bending, then the inference we draw from that is that the Earth wouldn't have a gravitational field. There would be no gravity. It's the bendiness of space for Einstein, and the fact that space can be warped is what it is that makes it possible for gravity to exist. The other thing that has to happen is that the shape of space has to change as the Earth moves. Because if the Earth rolls but it leaves this kind of trench behind it, then its gravitational field would have this kind of weight that was left behind it, which is not the way gravity behaves. The Earth's gravitational field follows the Earth around. It's very well behaved like that. It's not, how many people here have seen Peter Pan, the movie? There's a scene in that where Peter Pan loses his shadow. No, is it Peter Pan or is it Tinkerbell? Loses Peter Pan, right? I just testing. And so he becomes detached from his shadow. I mean, we know that's something that's kind of fantastical and cartoony. But if the Earth, if the shape of space didn't keep up with the Earth as it moves around, then the Earth would become detached from its gravitational field in the same way that Peter Pan became detached from his shadow. So we know that as the Earth moves, we know that space has to kind of spring back into its original positions as the Earth goes away. So we know that space is something that's both bendy, but also stiff, and that it returns to its original shape. And so this is all kind of implicit in Einstein's theory of relativity. It gives us a new understanding, and it's more complex because in order to understand what gravity is doing, we have to be able to kind of mathematically describe the changing shape of space, which is why general relativity has this reputation, its well-deserved reputation for being reasonably hard. So I'm not going to show you any equations. But what I want to do is I want to show you that what this does is it changes our understanding of the way that gravity works, but it does that by changing our understanding of the way that space and time work. Space and time are now things that will change, that will themselves change as things happen inside of them. Whereas for Newton, space and time, were just there to tell you what was going on. They weren't part of the game. They weren't part of the show. So, lightning introduction to general relativity. So, this gentleman here is Karl Schwarzschild. It turns out in 1916 he was an officer in the German army. He got sick while he was serving on the Russian front, and he was in a hospital. He eventually died there. Not long later, he had a very unpleasant skin condition, apparently. Didn't know that you could die of a skin condition, but apparently it's possible, at least in 1916. And so, but to kind of cheer himself up, he was reading the article that Einstein had written in a journal, and he taught himself general relativity. And he not only did that, he solved Einstein's equations for the gravitational field of a single spherical object. So in Newtonian gravity, that's really easy. It turns out in Einstein gravity, even solving that requires something. you find, or what he found, or what you find when you look at this solution, is that there's a magical radius, this distance that when you're, if you, in the case of the sun, it's a sphere about 3 kilometers across. And if you imagine packing all of the sun into a single point, and then within 3 kilometers, the distance, this is the edge of the black hole that the sun would make. So he didn't talk about this at all because he didn't imagine that any physical object could be built that would be living inside of what has become called the Schwarzschild radius. So for him, this was kind of a mathematical curiosity. It wasn't something that was, that was a prediction. But the equation that he wrote down in 1916, the hospital somewhat back of the Russian front, is the equation that we would now take to describe the physics of a black hole that is not rotating. So 100 years later. So the mathematical formula for a black hole was first written down in 1916, even though it wasn't fully realized at the time what its implications would be. So we'll now fast forward. So I'm going to jump around a bit, no one gets motion sickness. But we're now going to be in the early 1960s, and we're now living in Texas. So we've moved Berlin to Texas. And it was in that time, or in Texas, particularly in Texas, that the field of what was called relativistic astrophysics was starting to be sort of taken seriously. And the thing that was being taken seriously is that we were starting to see objects in the sky. So by the late 1930s, it had been sort of guessed prior to that, it had been guessed that nuclear reactions took place inside of stars. The sort of detailed physics of those reactions had been worked out in some detail by the end of the 1930s by Hans Bethe, among others. But it was really only in the 1950s and 60s that people were seeing objects in the sky that was starting to make them think that things like neutron stars, things like black holes, that those things may actually have some physical reality, that they're not simply a kind of mathematical artifact, an artifact of these theories that have been written down over the previous, I guess going back to 1905, if you want to go back that far. And so just as an aside, one of the people who was in Texas at the time was New Zealander Roy Kerr, who wrote down the more general form of a black hole, the same problem that Schwarzschild solved, but for the case of a black hole, that's the object that created it had some spin around its axis. And so he wrote down the solution to the Einstein equations that describe the spinning black hole in 1963. He was working in Texas. Another New Zealander who was there at the time, in fact, was Beatrice Tinsley. So she didn't work directly on black holes, but she was again sort of part of this flowering of activity that took place in Texas in the early 60s. Okay, so this gets us through to the fact that the phrase black hole itself was first used in the late 1960s by John Wheeler, who was a well-known American physicist. So this gets us through to the point where we've got the idea of black holes. We're starting to see things in space that are very intense, very small, very localized, strong gravitational fields, very short. Objects that change, who are very bright, but whose brightness changes rapidly with time, which again tells you they have to fit in a relatively small space. We're just starting to see these objects over, we're starting to find things like pulsars and quasars, so we're starting to think that we have to take these objects seriously. And so when you're doing this, there are two different things that you're trying to do, depending on who you are. If you're someone who's primarily interested in physics, you might be asking yourself, how does gravity work? So, we've got general relativity, but we want to know whether or not it's true. The other thing you might, another way to put that, was Einstein right? The other thing you can say is, what can we learn about ultra-high energy physics? It costs a lot of money to build a particle accelerator, but can we learn things the same questions that people try to ask at CERN, in Geneva? Can we ask these questions by looking at things that are going on in space? If you're an astronomer, on the other hand, maybe you really like just knowing what there in the sky. So that, we know that there are stars, we know there are planets, we know there are nebulae, what else is there? What goes on at the centre of galaxies? Because we know that weird stuff happens. So what kind of things happen? What happens to big stars when they die? What did the first stars look like? All of these are questions, where do the chemical elements come from? All of these are questions that you could reasonably ask about the evolving universe. And all of these are questions that it turns out that when we study black holes, that some of the answers to those questions are buried in. Okay, so I was asked to give you an update on gravitational waves. So how many people here have heard that there are these things called gravitational waves? Not bad, actually. You do better than my students. All companies, we have to all get paid. I'm just going to show you one photo of a detector. This object here is the LIGO, one of three gravitational wave detectors that are working fully operational at the look right now. These things are, the arms of this thing are 4 kilometers on a side, and what it's working to detect is it's working to detect ripples in space itself that are formed not only by the presence of a black hole, but where two black holes merge and collide. And so when that happens, or when that burst of gravitational radiation comes past the Earth, everything inside kind of wobbles, or everything that passes sort of wobbles a little bit like a jelly. And we can measure very accurately the differences in the lengths of these two arms. They change by about 1 part in a million trillion, the length, which is much, much less than the width of a single atom. And with lots of cunning optics and various other things, we can actually see these changes exactly. So LIGO sees, what LIGO sees is the most intense way we know to generate gravitational waves is when two black holes meet each other, merge, and form a single black hole. And so what LIGO sees, and so the first detection was in 2015, what LIGO sees is something like that. So on September